Today we study rotation matrix. First, we consider active transformation. In mathematics, we usually use the passive transformation, but in physics, the actual vector rotates instead of basis rotates. So, first we introduce the original basis set to express a vector in terms of Cartesian components x1, 2, 3. We like to rotate a vector x by rotating it about the z-axis by an angle of theta. And we would like to express this resultant vector x prime in terms of the original basis. That's the basic idea. Before the rotation, x vector is a linear combination of these three basis vectors. After the rotation, it will be expressed in terms of original basis vectors, and the Cartesian components transforms from the original values to the resultant values. If we keep the Cartesian components the same, the resultant vector can also be expressed in terms of a new basis that are actually rotated. In that case, relative to this rotated basis, the Cartesian components are invariant. So there are two ways of expressing a rotated vector x prime. This is to keep the basis vector the same and components different. Another way is to keep the Cartesian components the same but rotating the basis vector. In any case, the two results must be the same. We consider by making use of the completeness relation, in this problem, we restrict ourselves to the two-dimensional case instead of the three-dimensional case. So in two-dimensional case, we have only two basis vectors, E1 and E2, or E1 prime and E2 prime. In our strategy is to keep the original basis set the same before and after the transformation. So we'd like to express any arbitrary vector as a linear combination of E1 and E2. And the coefficients that are Cartesian components, this is A1 and this is A2. This is the reason why we keep using unit basis vector. We do not have any denominator vector. Okay, so we first compute the directional cosines. The scalar products 1 and 2 and 1 prime and 2 prime. We'd like to compute the scalar products among them. First of all, E1 and E1 prime. Before the rotation, the unit basis vectors were E1 and E2. So E1 has been rotated to E1 prime by an angle of theta. So scalar product of E1 and E1 prime is a cosine theta, trivial. Next, we consider E1 prime and E2. E1 prime is here and E2 is here. Because this is a right angle and this is a theta and this is 1/2 of pi minus theta. So its a scalar product is a cosine of a pi minus theta. For any real number theta, it is a sine theta. Okay, next we consider E2 prime and E1. E2 prime is here. It has been rotated from E2 by an angle of theta. The angle between E1 and E2 prime is, because it is a right angle, the angle is 1/2 of pi plus theta. Therefore, it is minus sine theta. E2 prime and E2, their scalar product is trivial, just like the E1 prime and E1, because it has been rotated from E2 to E2 prime by an angle of theta. So this is cosine. We substitute these values for the directional cosines that appears in the expansion of E1 prime by making use of the completeness relation that we just listed here. Substituting A equals E1 prime, what we obtain is E1 plus E2 with the coefficients. They are determined in here, and E2 and E1 prime here. So it's cosine plus sine with the basis vectors E1 and E2. What about E2 prime? E2 prime can be expanded again in terms of E1 and E2. Their coefficients are here, and we can copy E1 dot E2 prime is here minus sine theta, and the E2 prime, that is cosine theta. That's fine. As a result, I can make a matrix, make use of a matrix to express these two relationships in a compact form. First of all, we can write it, this one as a cosine sine stand up E1, E2. Here, minus the sine, cosine, stand up E1, E2, E1 and E2. And copy this one first as a first row and as the second row. And we have a common factor. As a result, we have found the relationship among the old basis vector and new basis vector. But I'd like to keep using the original basis vector. By the way, we previously noted that the original vector can be expressed in two ways. After rotation, we can keep using the original one, then the coefficients may vary. However, in here, if we keep the coefficients the same, then what I have is a different basis vector that has been rotated. But we just have found is the relationship among the prime, the new basis, and old basis. So we, as a first step, it's better to use this notation to make use of our result. Therefore, we can make use of this. Let's see. A prime, we can keep the original Cartesian components as it is and multiplied by new basis vector. However, I can replace this one with the right hand side. So if I substitute this value for this column vector, this is just a copy. Then I have row vector Cartesian components, and then this one is replaced with this. Therefore, matrix and column vector. So let us see. U vector can be expanded as a linear combination of a new old basis vector. So from here, I can read the result of what? This. Like what I wanted to find is A1 prime, A2 prime in terms of old basis vectors. This one is the same as the rotated resultant vector. As a result, what I find is because these bases are the same, and the reason why we keep using the basis vector to represent the vector is because the coefficients are uniquely defined. Therefore, from this identity, I can read off this U Cartesian components by making use of the old Cartesian basis and rotation matrix. Okay, so what I have just found is this new basis, new Cartesian components expressed in terms of old Cartesian components multiplied by this. By the way, a usual way to find out express the Cartesian Cartesian components are usually column, the form of the column. So it's better to replace this row vector as a column vector. If I replace a row by a column for a single row, it's fine to just convert this row as a column. However, if they are multiplied form, in that case, what I need to do is this one convert into a column, but this column is multiplied to the row, so this column is replaced with row, and this column is replaced with row. So if I copy this one first, A1, A2, and this column is cosine minus sine, and this column is a sine cosine. So if I apply the transpose, that is to convert the row to a column and convert a column into a row, in that case, what I need to do is take the transpose and attach it to the right hand side. The reason is that the row is multiplied only on the left, and a column is multiplied on the right. That's the reason why the order of multiplication is exchanged. Okay, so this row vector has been transformed into column, and these two columns has been transformed into the rows. As a result, if you learn mathematics, you will find that this is a general relationship for the computing the transpose of the product of matrices, but here it's enough. So finally, if I write in this manner, U Cartesian coordinates in a column vector can be expressed as this is a matrix, and now we call the rotation matrix. Even though we have started our computation by making use of basis vectors, in practice we are more interested in the components only. So in physical analysis, we usually denote the rotation matrix of Cartesian components, rather than the rotation matrix for the basis vectors. So rotation matrix for the Cartesian components from original one to the resultant one is denoted by matrix R. And if I read these four components, elements, first 1, 1 element, 1, 2 element, and the 2, 1 element, and the 2, 2 element. And they are just copied from our previous result. So we had better memorize the form of these 2 by 2 matrix for the rotation on the 2 dimension. By the way, we recall the directional cosines that we evaluated in here to construct the relationship among the original basis vectors and the rotated basis vectors. So we make use of that to find that these are actually the directional cosines. You find the first column is related to E1 prime, and second column is related to E2 prime. And if you copy these two, you can construct that E2 prime. If I multiply this one by E2 prime, that E1 dot E2 prime, something like that. And here E2 prime that E2. If I sum these two, what I find is after E multiplied by E2 prime, then this one represents nothing but E2 prime vector. And this one, in a similar manner, it is a E1 prime vector. So we expect that this column, they represent the E1 prime and E2 prime. And we know these two Cartesian basis vectors are orthogonal to each other. We can see here components of cosine and sine, and minus sine and cosine. These two are orthogonal. If I compute the scalar product between them, then I just convert it as a row, CS, and copy this column. What I find is a cosine sine, negative sine, and sine cosine, positive sine is 0. What about the square of this single column? Because it's a unit vector, its square is 1. Let's see what happens. I copy this one, cosine sine, stand up, cosine sine, multiplications, cosine square, sine square, 1. What about this? This one too. So every row or column of a rotation matrix, a unit basis vector, and they are all orthogonal. That's the reason why the inverse matrix is trivial to obtain. And actually the transpose is the inverse. We will find after that. So this is just a reproduction of what I just have told you about the completeness relation. And we consider the case of a three-dimensional case. And actually, what we have found is this 2 by 2 matrix that can be obtained by rotating the vector, a vector about the z-axis. So in three-dimensional case, it's better to introduce an axis of rotation. So if the axis of rotation is the z-axis, then this rotation matrix representing the rotation about the z-axis can be expressed in this manner. We can see z, if we rotate it about the z-axis, it doesn't change the z component, except that x and y components varies covariantly, systematically, consistently. So show that identity matrix, 3 by 3 identity matrix is a metric tensor. Metric tensor is nothing but when we define a scalar product, the scalar product is very close to, has the close relationship with the definition of length of a vector. The a vector scalar product to itself as square root, it is the length or magnitude of a vector A. Therefore, if I introduce a matrix notation to represent a vector, then in some case we need to insert some matrix to find out the magnitude. So A1, A2, A3, A1, A2, A3. In Euclidean space, if I introduce a Cartesian components, it's nothing but A1, A2, A3, A1, A2, A3 to obtain the square of a vector. In a similar manner, I can multiply these two to compute the scalar product of any two vectors. By the way, we can insert this strange matrix that are all vanishing except for the diagonal components. If I insert this matrix, the result is the same. That is A1, B1, A2, B2, A3, B3, and sum them all. Let's see. If I multiply this column, here, the first element is a B1. If I multiply this and this, what I find is a vanishing, and it projects out the middle. And then, if I multiply to here, the result is a B3. Therefore, B1, B2, B3, so it is identical to each other. So, a matrix that can be inserted to obtain the scalar product of two vectors. One is expressed as a row vector, and the other is expressed as a column vector, is called metric tensor. It is a related meter, measuring the length. Okay. E3 is invariant under this transformation. Okay, our rotation matrix about the z-axis is expressed in this manner. Or if I multiply arbitrary vector, let's see what happens. Here, z component doesn't contribute. So this is the same for the two-dimensional case. And then A3 is invariant. Okay, so the vector E3 is nothing but 0, E1, 0, E2, and 1, E3. So if I express this a vector in Cartesian components, the components are 0, 0, 1. If I multiply 0, 0, 1 to here, it is still 0, 0, 1. So this one shows that any vector parallel to the axis of rotation is invariant on the rotation. Next, we consider the case the inverse is nothing but the transpose. This is a very, very special nature of the rotation matrix. Let's see what happens if I take the transpose. Transpose is to transform this column into rows. Cosine, sine, and minus sine, and cosine, and 0. Okay, the third column is shifted to the third row. That's fine. So let us multiply these two matrices, rotation matrix and transpose. And multiplication of two matrices can be made. Just to choose the rows, just to choose columns that appears in the next. Okay, cosine, cosine, sine, sine, 0. So next, keep using the first row, then cosine minus sine, sine, cosine. Okay, cosine minus sine, okay, and sine, cosine. So that's it's 0. The third one, this 0, 0, 1 multiplied to cosine sine 0, oh, 0. Next, minus sine cosine, in a similar manner, just like this, it vanishes. Next one, minus sine squared, so it is sine squared, and cosine squared, and third one is a 0. Okay, that's fine. And then, next one also vanishes, 0, 0 kills the sine and cosine. The third row and third column survives, except that third row kills the first and second column. Finally, what we find is everything is a 0 except for the diagonal components that are all 1. So it is nothing but the identity matrix. Okay, we can do the same job by exchanging the order, and the final result is identical to each other. Therefore, if I have a matrix X such that product with A, there are two ways to multiply, and both of them gives the identity matrix, then I would say it is inverse matrix. So, multiplicative inverse of matrix A. Therefore, rotation matrix transpose is nothing but the inverse of the rotation matrix. Next, we consider determinant. Determinant is closely related to the area for the 2x2 cases and the volume spanned in 2 dimensions. We have 2 rows. We can think of 2 vectors on a plane, and the area of this parallelogram spanned by these 2 vectors, and these 2 rows or columns can represent the Cartesian components of these 2 vectors, and Cartesian components of these 2 vectors can be treated to be each row or column of the matrix. In that case, the area of this parallelogram is nothing but the determinant except for the sign. It depends on the orientation we choose. Okay, in 2x2 case, determinant is defined by this complicated expansion, and we have coefficients. First, we choose one element from the first row, and another element from the second row, and we find 1, 2, 1, 2 in every term. Okay, choose one element from the first row, choose another element from the second row, and we vary 1, 1, 1, 2, 2, 1, 2, 2. That means you can choose either of these 2 elements. You can choose either of these 2 elements from the second row. So we have a choice of 2x2 is 4 possibilities. Among them, we only keep the permutations. They should be different. So same thing, 1, 1 and 2, 2. Go away. We don't like it. There are 2 left. This is called the even permutation, 1, 2, and this is an odd permutation. Any even permutation is 1. For example, this is in 2-dimensional case, there is only a single permutation, that is 1, 2. And if I exchange the order, the final result is negative sign. Therefore, in the 4 terms in the expansion, we only have 2 terms, And one term is diagonal product, and the other term is off-diagonal product with a negative sign. So if you make use of this definition, the determinant of a two-dimensional rotation matrix is we have cosine sine minus sine cosine. Determinant is a product of this cosine square, product of this minus sine square multiplied by negative sine. Therefore, cosine square plus sine square, that is 1. Okay, so this one shows that volume of this guy, the area of a parallelogram doesn't change its area after the rotation. The determinant keeps the area of a parallelogram in 2 dimensions. What about the case for the 3-dimensional one? In that case, it can be generalized to compute the volume of a parallelepiped spanned by A, B, and C vector. And actually, this is triple equivalent to the triple scalar product, that is cross product, scalar product. And that is represented by this. And Lebesgue tensor for this 3-dimensional case has 6 non-zero cases. They are permutation of 3. And among them, we have 3 is 3 times 2. We have 3 even permutation and 3 odd permutations. 3 even permutations are this, and 3 odd permutations are this. And among all 3 times 3 times 3, 27. A lot of terms, only 6 terms, and the 3 by 3 positive and 3 negative, and 21 pieces are all vanishing. In this special case for the rotation about the z-axis, if you insert all of these coefficients, you will find it's identical to the 2 by 2 matrix, because this is 1, and these kills everything, and it is truncated into a very simple one that we already have computed, that is to be 1. Therefore, if you rotate a parallelepiped, the volume is invariant. That's it for today.